Okay, we're going to talk about polyprotic acids today. Uh, this is video number 2 in the series of the While We're Stuck at Home videos that I'm making for AP Chemistry. As you see in this slide, we have sulfuric acid, and you can see the Lewis structure over here, and an example of the stuff here. It's a clear acid, and the formula is H2. You can see that here, and then SO4. And it's one of the strong acids that's polyprotic. We're going to look at some weak ones today and how to calculate the pH of those. And a little more complicated, but it's as everything in this class, it's not bad once you see a couple of examples and try them. So let's move on here. Polyprotic acids are acids that can furnish more than one proton, like H2SO4. Phosphoric acid is the one we're going to look at today, which is H3PO4. They always dissociate in a stepwise manner, meaning one proton or H plus ion at a time. The conjugate base of the first dissociation equilibrium becomes the acid in the second step. So that's where we get some weirdness in this, but once you start seeing how the equation's set up, it's not too bad. For a typical weak polyprotic acid, the first dissociation constant is greater than the second, is greater than the third, so they get progressively weaker as you go. For a typical polyprotic acid and water, only the first dissociation step is important to the pH. However, they could ask you about concentrations for the anions, as you're going to see in this example that we're going to look at today. So let's look at this. It says calculate the pH of a 1 molar solution of H3PO4. And before we do that, I just want to take you through the equations that occur for all three of these Ka values. You notice the first one is the largest, Ka1, and that relates to this equation where you've got phosphoric acid. It's losing one of its protons here, and then you end up with H2PO4 minus, which is the conjugate base, the leftovers from the acid. In the second Ka setup, you notice that conjugate base that's here ends up over here, and we get another H plus dissociation and a new conjugate base, which goes into the third one. So you see that the charge goes from 0 to -1 to -2, and the charge on the anion increases until you end up with phosphate here at the end. So calculating the pH of this thing involves looking purely at the first K value because the pH is always going to be from that. The amount of H plus in the solution is not increasing. It remains constant. And so even though we have it dissociating stepwise, going from the first K value will give us essentially all the H plus that's in there since it's so big compared to the rest. So doing that, we look at that first equation that I showed you guys. We set up, as always, the ice table. The ice table here, we're starting with an initial of that 1 molar, 0 of those guys again. Remember that we don't know the change, so we substitute X in for that. And so initially 1, the change is X, negative on this side, positive on the product side, and at equilibrium, we have a 1, remembering that the K value is small enough to disregard the change for the phosphoric acid, and we have X and X there. Setting it up into our Ka expression, we put in the Ka value that was given earlier, plug in the 2 X's from there and there, plug in the 1 down there. That should be 1.00, but it doesn't matter. This times that is pretty easy. Most of us can do that one in our head. We end up with X squared equals this, since it's times 1. X equals about 0.087. Now, if you do the quadratic for this one, you're going to get a lower number slightly, but it's not enough to really mess us up. So I went ahead and did it the easy way, as I suggest my students do. Negative log of that gives me a pH of 1.06. It's clearly acidic. And that's how you get the pH of a weak acid. Notice there's really nothing different, but here's the rub, as they say. Things can get a little weird when they start asking you for concentrations of the anion in the solution. Okay. So here it says calculate the equilibrium concentration of phosphate in a 1 molar solution of H3PO4. And again, going back to those equations, I'm going to take us back a few slides here. Notice the phosphate doesn't show up until the third Ka. So we've got to take and go through all three of those to get there. Well, two of them to get to there. So we're going to show you how to do that in the next couple slides. Let me go back here. Okay, so remember in the first one, we ended up with 0.087 for this ion, which is the conjugate base of H3PO4. It becomes the new acid, as we said earlier in the notes. So that's 0.087. This is also 0.087 because this was in a 1-to-1 ratio with this. So if you go back and look at that, if you substitute X in, you end up with that. What's not in the solution at this point is this ion initially. So as we go through this thing stepwise, we have to start doing some work with that. Well, that's going to get us to these guys being essentially the same. Disregard the changes for those guys because they have numbers and it's not big enough to worry about. But this one we want to have set up. Okay. So you put it all in the expression, you're going to get X equals 6.2 times 10 to the negative 8 moles per liter. Now, this is a really important topic because if we go back, you notice that the Ka2 is 6.2 times 10 to the negative 8. So here's a lesson to be learned here for later when we get into chapter 15. When the acid concentration and the H plus concentration are equal to each other, the X for this guy is always going to equal the K value. Let me say it again. When the acid and the H plus concentrations are equal, X equals the Ka value. Okay, so it's going to be the same thing. Okay, for the third step, which is to get us into the phosphate, that means we start out now with 6.2 times 10 to the negative 8. If we go back real quickly, that X solved out gave us this. So we're going to carry it into the next ice table. So here we have that. Notice earlier I said the H plus doesn't change throughout all of this, so that gets to stay like that. Okay, we're going to get a minus X there, a plus X there, disregard, we end up with X there. Okay, so we're basically solving for X again. In this case, you notice how small this is. It's 3.6 times 10 to the negative 19. That's what our X value is going to be when we plug everything in. And that's the answer to the question. So there's very little phosphate ion in there at that point, which makes sense because the K value is super small for that. So that's basically getting, oops, I'm going to skip to the next topic. That's getting some questions answered for polyprotic acids. Don't let them scare you. It's just basically get the pH from the first Ka. If they start asking you about the anions, just solve until you get to that anion. Do your ice table, do your K expression. Nothing changes from what we've been doing up to this point. It's all the same method. Set up the K. Get the ice table set up if you need the ice table. Plug the numbers into the K expression. Solve it. Figure out what the X stands for. And then use it appropriately. Okay.